All right, in chapter 6, we covered discrete random variables, and specifically we talked about the binomial. Okay, there are lots of other kinds of discrete random variables, okay, but the binomial is the most important, so that's the one that we focused on. We have a similar kind of thing in chapter 7. We're going to be covering continuous variables in chapter 7, but we're mainly going to talk about the normal random variable. Okay. There are lots of other kinds of continuous variables. Like one of the variables that is talked about in 7.1 is the uniform variable, so the uniform distribution, but we're actually not going to cover that. And there are other kinds of continuous variables as well, but we're just going to focus on the normal variable because that's the most important one. That's the one that comes up over and over and over again in this course. So a couple things about continuous variables, okay? With discrete variables, we were able to compute the probability of x being a particular value. Like we were able to compute probability that x was 2. With the continuous variable, this is not possible, or it's just not super meaningful, okay? The probability of observing one particular value is always 0 when you're dealing with a continuous variable. And the reason for that is if you have a continuous variable, there are always infinitely many possibilities. And if you're looking at the probability that looks like 1 over n, where n is allowed to get as large as you like, right? It's allowed to go to infinity. And if you think about what happens to 1 over n as n goes to infinity, so as n gets larger and larger and larger, 1 over n gets smaller and smaller and smaller, right? Like 1 over 100 is bigger than 1 over 1,000,000, right? So as n gets big, this thing goes to 0. And that's what happens when you're dealing with continuous variables, because with continuous variables, there are always infinitely many possibilities. So to resolve this issue, we compute probabilities for continuous variables over an interval, rather than for a single value. And then we find the probability that x is within that interval using what's called the probability density function, or PDF for short. Deriving PDFs is not an easy task, so I'm not going to give you a ton of reasoning behind how we get these functions. But what you do need to understand is that the probability that x is within a certain interval is equal to the area between the graph of the PDF and the x-axis over that interval. And if any of you have ever taken calculus, then that concept should sound familiar. That's just an integral, right? So if you want to know the probability that x is within a certain interval, then you integrate the PDF over that interval, and that's equal to the probability. If you're not familiar with calculus, don't worry about it too much. We'll see in StatCrunch kind of how areas and probabilities are correspond to each other. Okay. Now, for your information, this is the probability density function for a normal random variable. We're not going to be using this formula directly, but just to kind of show you why we don't do the work by hand on these, it is of course possible to do the work by hand, but it's not easy. You have to have calculus. You have to understand calculus in order to understand how to compute probabilities involving the normal variable. And so since most of you probably haven't had calculus, we're not going to talk about it. But this is the function, for those of you who maybe have had calculus, this is the function that you would integrate over a particular interval to determine the probability that x is within that interval. What I want to point out to the rest of you is that this function relies on mu and sigma. It's dependent on mu and sigma. Okay, and if you think about basically at its core, this function is an exponential function, right? It looks like f of x equals e to the x, but there's some stuff that's being done to the variable here. But if you think about what happens to this function when you subtract values from it, that moves the function, that shifts the function to the right. So mu, as it turns out, if you were to graph this function, mu is the high peak of our normal distribution. So a normal distribution is just kind of, it's another way to say that you have a bell-shaped distribution and the mean is going to be right in the center. And you can see that here because this shifts the graph left and right. It's going to shift the peak of the graph over to where mu is. Now, sigma, your standard deviation, that tells you how spread out the data is, right? We learned that in chapter 3. The way that it affects the graph here is that if you're dividing by sigma, then that's going to have a tendency to either compress the graph and kind of stretch it out vertically, or to compress it vertically. And so that corresponds nicely to what we know about sigma and what we know about the standard deviation, right? Anyway, in this section, we're just going to practice drawing some normal curves and then shading in some areas corresponding to normal curves. It's really a pretty short section, and that's because we're skipping the stuff about the uniform distribution. But in the next section, in 7.2, we'll talk about actually computing probabilities involving the normal variable. But anyway, here's what I was saying before, right? So here's a normal distribution with mean 0. And then here's a normal distribution with mean 3, right? So you can see it gets shifted to the right 3 units, which makes sense based on what the PDF looks like, what that function looks like. And here's a normal distribution with a standard deviation of 1, right? And then here's a normal distribution with a standard deviation of 2. So you can see spreading out the data. Okay, so let's just practice drawing some stuff. So this first one says the weights of giraffes are approximately normally distributed with mean 2,200 pounds and standard deviation 200 pounds. Part A asks us to draw a normal curve with the parameters labeled, then shade the area under the normal curve to the left of 2,100 pounds. Okay, so to draw a normal curve, give yourself an x-axis, and then we can draw our little bell-shaped curve. You could probably do a better job than what I just did, but that's okay. The mean should go right in the middle of the graph, right at the high point of the graph. So this is the mean, and we're told the mean is 2,200 pounds. Okay, so that's the mean. We're also told the standard deviation is 200 pounds. So if you're 1 standard deviation above the mean, then you're at 2,400 pounds. 2 above puts you at 2,600, and 3 above puts you at 2,800. I'm not too particular about where exactly these tick marks are. As long as you're putting 1, 2, and 3 standard deviations from the mean, I'm happy. So 1 standard deviation below would put you at 2,000, 2 below 1,800, and 3 below puts you at 1,600. Okay, so here's mu plus sigma, mu plus 2 sigma, and so forth, right? Mu minus sigma, mu minus 2 sigma. Okay, so there's our normal curve, and then it says to shade the area under the normal curve left of 2,100 pounds. So 2,100 pounds would be right here in between 2,200 and 2,000, and there's the area that we were asked to shade in. Now, under the normal curve, to the left of 2,100 pounds is 0.3085. So in other words, they're telling us that this area right here, they're telling us that that area is 0.3085. Now they say provide 2 interpretations of the result. Okay. So one area corresponds to a probability, okay? So one interpretation would be to say that the probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.3085. Or another way to say the same thing is to say, like, there's a 30.85% chance that if you randomly select a giraffe, it will weigh less than 2,100 pounds. Okay, so I'm going to say the probability giraffe weighs less than 2,100 pounds is 0.3085. Okay, so there's one interpretation. Another interpretation. Interpretation 2. So another interpretation would be to say something like 30.85% of giraffes weigh less than 2,100 pounds, right? Okay, that's just an equivalent way of saying the same thing. But the moral of the story and the whole sort of point of going over this stuff in this section is just so that you realize that 0.3085 is equivalent to the probability that a giraffe is less than 2,100 pounds. Okay, so that's the idea there. There's a little homework assignment for you, and we'll see you in 7.2.